Okay, so in the last couple of videos, we have been developing kinematics in a non-inertial system. And so now we want to go ahead and take a look at dynamics in non-inertial systems, but specifically in rotating coordinate systems. Okay, so what we came up with last time is that in the inertial frame, we can express the force as being equal to the mass times the acceleration in the non-inertial frame plus m omega dot cross r prime plus 2m omega cross v prime plus m omega cross r prime plus m a naught. Okay, we can rearrange that to get that into what the rotating observer, or what the non-inertial observer would say. The non-inertial observer would say the net force that he or she measures, F prime, is equal to our F from before. And then we just subtract all this stuff over here on the right-hand side. So minus m omega dot cross r prime minus 2m omega cross v prime minus m omega cross r prime minus m a naught. Okay, and they would say that that equals m a, whoops, let's try that again. They'd say that equals m a prime. So each of these has names, so these are the physical forces. And then following from before, this is the transverse force. This is the Coriolis force. This is the centrifugal force. The acceleration is called the centripetal acceleration, but the force is called the centrifugal force. And this is the inertial force. Okay. And to an observer in an accelerated frame, all of those are real. So I think we treated the effect of the inertial force before, so I don't really need to look at that now. But I would like to get a feel for how the other three forces would point. So the example I'm thinking is that we're on a turntable, and let's just go ahead and make it rotate counterclockwise. So then omega will point out of the page. And here, let me just totally redraw this. It's already turned into crap. Okay, so let's make a big turntable. Much better. All right, then we're going to make it rotate like so. So then my rotational velocity vector points straight out of the page. Here's my point of interest. So there's my r prime. Okay. So let's go ahead and work out the direction of the Coriolis force. So that will be minus 2m omega cross v prime. So in this case here, let's say there's my omega. Let's just make v point like so. So then you should be able to convince yourself that omega cross v we'll point at right angles like so. And since we need the negative of it, the Coriolis force will point, in this case, off to the right of how you're going. While we're at it, we can work out the transverse force. So here, let's go ahead and assume that omega dot is positive, and we were looking at our v prime being radially outward here. So to get our transverse force, that would be equal to minus m omega dot cross r prime. So in this case here, since omega dot is positive, omega dot will also point out, like so. Here, let's get a little more room. So omega dot points in the same direction as omega. There's my r prime from before. So omega dot cross r prime points that way. And again, because of the negative, the transverse force points like so. And then finally, let's get the centrifugal force. So remember, that was equal to minus m omega cross r. So there's my omega pointing out. There's my point of interest. There's my r prime there. So then omega cross r prime will point like that. Need to move that over there. And then omega cross r prime will be pointing in, but the force is the negative of that. So it points out. All right, so we see here that the centrifugal force is basically trying to throw the object off the turntable, so it points away from the center. All right, now let's go and take a look at some other cases. Let's say that, so we'll keep here omega dot, now we'll say is so we'll say that now the rate of rotation is decreasing, but we'll still keep v prime radially out. So in that case, you should be able to convince yourself that the Coriolis force and the centrifugal force are the same as before. The one that will be different is the transverse force. So let's do that one. So omega dot will be pointing the opposite way of omega, so it's going into the page. There's my r prime. So now omega dot cross r prime is pointing like that. So the transverse force now is pointing the opposite way it did before. So before, when we were speeding up, the transverse force is kind of trying to make you go clockwise-y. Now when we're slowing down, it's trying to make you go counterclockwise-y. All right. Let's go ahead and repeat for the case of v prime being radially in. The transverse force is the same as the previous two cases because it doesn't depend on v at all. And also, the centrifugal force doesn't depend on v at all, so that will be the same as before. So that just leaves us with the Coriolis force. So for being radially in, we're going to have, there's my omega pointing out. That would be my v prime now, so that would be my omega cross v prime. And then that would be my Coriolis force. So again, it's trying to move you to the right for our clockwise rotation. Okay, now finally, let's look at what happens if we're rotating clockwise instead of counterclockwise. The transverse force doesn't change at all. It'll just follow from the first two cases. And that's because it just depends on the direction of omega dot. Now here, obviously, we would be reversing the role of speeding up and slowing down. So I'm just saying for the given direction of omega dot, the transverse force is still doing what it does. So that does affect our centrifugal force, though. So let's go do that one next. That one's a little easier. So to get our centrifugal force, omega is pointing in like so. There's my r as before. So omega cross r points that way. Omega cross r points that way. And the centrifugal force still is trying to basically throw you out. And that doesn't matter if the velocity is radially in or out. The one that does matter is the Coriolis force. So let's look at the Coriolis force now. If the velocity is radially out, we can go ahead and do our cross products here. We'll have omega pointing in, v is pointing out, so omega cross v points that way, and the Coriolis force points now to the left. And if v is radially in, we'll have our omega like so. There's my V. So that's omega cross V. So the Coriolis force now would again point to the left of the way you're going. So I think we can try to summarize this like so. If omega dot is positive, then we can say that the transverse force points, we'll say clockwise-y. Obviously it's pointing a straight line, but it'll point in the clockwise type direction from that point. And likewise, if it's negative, the transverse force points in the counterclockwise-y kind of way. No matter what, the centrifugal force, yeah, you can do that better. Always points outward. And if our rotation is clockwise, the Coriolis force points to the right of V. And if it's counterclockwise, it points to the left of V prime. Okay. So let's just do a application of this to get some feel for it. Let's look at cyclonic motion. So we're talking about the general motion of the air in the atmosphere. So if we look at how the Earth rotates, so we'll make this North America, and then, oh God, that's terrible. I can do a better South America than I can in North America. There's South America, and then I'm just going to tell you that blob there is North America. Anyway, to remember which way the Earth spins, just think of the wedge that Brazil makes going into the Pacific Ocean as spin this way. So that means that our angular velocity points out through the North Pole. In fact, that's how you define the North Pole of a planet. So let's now look down on the northern hemisphere. In that case, the angular velocity will be pointing out of the page. So now let's say you have a low pressure cell, or low pressure center right there. The air around is in a higher pressure region, so it's going to want to fall in towards the low pressure center there. That's good, but then if we figure out the direction of the Coriolis force, we see that since from our perspective the Earth is turning counterclockwise when viewed from above, that's going to deflect the air to the right of its motion, like so. Now it would want to keep churning away, except that you've got some surrounding high pressure air keeping it deflected back in, so it'll do something like that. And then we can kind of repeat this like so, just to get a little better feel for it. We'll just follow a few more streamlines, and the net upshot is that we get this counterclockwise rotation around the low pressure center. Obviously, in the southern hemisphere, the situation is reversed. By the way, this is not why toilet bowls swirl the way they do. In order to make sure that you have good flow, it turns out that you need the water to swirl in order to allow a channel for the air to get in and out during the flushing action. And so, in order for that to happen, the designers of toilets actually just plain give it a direction by the way they cut the jets. So, sorry to defeat that old saw, but unfortunately that's how it goes. And similarly, when you have people demonstrating that, you'll find if you ever travel near the equator, you'll have touts who will demonstrate the equator by showing water very gently swirling one way or the other while they let it drain out of a milk jug or something. They're actually just kind of giving it a very subtle little shake that you hadn't realized. This effect barely matters on any human-sized scale, but on a planetary scale, it does start to matter. And so this counterclockwise flow is what drives things like, say, the trade winds and the prevailing winds in different parts of the earth and stuff like that. It's a little more complicated than that, but we'll leave it there. Okay. And we'll also, just to do another example here, let's go and take a look at the motion of a hockey puck. On a frictionless merry-go-round. So we'll assume that our turntable is rotating slowly. Otherwise, things get messy. So we can take a look at the trajectory after the puck receives some kicks. So if we work in our primed frame, we would say our external force, well, that'll be 0 because this is after the kick, minus m omega dot cross r prime. Well, it's rotating slowly at a constant speed, so that's 0, minus 2m omega cross v prime. So the Coriolis force is going to matter here. Pardon me a second there. Yeah, the Coriolis force is going to matter, but the centrifugal force we're going to kind of wish away. So minus m omega cross r. We're going to say this is approximately 0 because since omega is already small, they'll make omega prime really small. And then there's no inertial force in the problem, so we can just drop that. That'll equal ma prime. So, canceling the m's, we get that our a prime is roughly equal to minus 2 omega cross v prime. So the force is always going to be perpendicular to V prime. So an observer on the turntable will see a circular arc. So let's say our omega is going like that. To an observer on the turntable, they would just see a nice little circular arc, like so. Now, let's redo this as an unprimed observer. So an inertial observer. They would just plain say that there's no force, so the acceleration is 0. So they would say it's a straight line motion. So here, turntable's rotating like so, and they actually see a straight line motion. A person on the turntable, they would argue, because of how the turntable is churning, will wind up perceiving the curve. Now, if omega isn't small, then we have to be a little more careful. If omega isn't small, we can't neglect the Coriolis force. Or sorry, to the centrifugal force. So you have to pay attention to that now too, which that's always trying to throw you outward. So again, in our primed frame, we'll just look at this at a couple different spots. Like say if I'm here and I give it a kick like so, we'll be seeing the Coriolis force pointing like so, and the centrifugal force pointing like so, and we would have to do some calculations. But on a different part of the trajectory, say where the kick, if there was a more straight lined out motion, then here we would be having the Coriolis force pointing straight to the right, and we would be having the centrifugal force pointing up, so they'd be at right angles. So the centrifugal force is always going to point out, the Coriolis force is always going to point to the right of how you're going right now. So the angle between the two could be anything that you please. So you're going to have that the acceleration measured in the primed frame will be minus 2 omega cross v prime minus omega cross r. That pretty much defies analytic solution, but it can be done numerically. Oh hey, I just happen to have done it numerically right here. So in this case, let's go ahead and make omega small like before, and you can see this is the nice circular arc that we were talking about right here. Now if I go and make omega bigger, like say 0.2, now we can start to see that we're getting some spiral action happening here. And this is because we're already probably to a point where we can't really neglect the centrifugal force. So let's go ahead and make it, say, 0.6. Now we're getting some kind of funky spiral. We could push it further if we want. But now here the spiral has bigger spacing. And now if we get to big numbers, we're starting to see that the centrifugal force is playing a big role, but the spiral still hasn't gone away. And if we go to absurd, we're still getting some sort of an arc here. So what we find is that we've kind of gotten to a balance between the centrifugal force and the Coriolis force, and they're both having their role to play. But it's definitely different than when we make the rotation, say, very small, and we just get these nice little circular arcs like we had before. So, unfortunately, it's just something that needs to be done numerically. There's really no clean solution otherwise. Okay, in the next pair of videos, we will be doing this to a very specific example of looking at the Earth's rotation and then leveraging that into describing the motion of the Foucault pendulum, which is one of the very few ways that we can actually prove that we live on a rotating Earth.